This lecture is going to talk about compressed sensing MRI. So compressed sensing MRI is based all on the idea or on the fact that medical images are compressible. And what that means, stated mathematically, is that if you project an image into the right domain, if you transform an image into the right domain, it should have sparse coefficients. Being compressible means that it has a sparse set of coefficients in some transformed domain, where sparse means that most of the coefficients are zero. So for example, mathematically we can write this way, that the image x here is equal to a sum of weighted basis functions phi sub I, where the weights are given by these alphas here, and they are specific to this image x. And they can be obtained mathematically by taking the inner product of x, the image, so this is like a vector of samples of the image, the inner product of that vector x with each basis function phi sub I. Here are some examples of some wavelet basis functions. So these, what you can see here is that you have like a large positive value here, a large negative value here. So this is a wavelet that is taking finite differences in the vertical dimension. It's sort of, you can think of it as taking finite differences in the vertical dimension. Likewise, this guy is taking finite differences in the left-right dimension, and this guy here is taking sort of diagonal differences. So what we mean by sparse is that when we take an image to some transform domain, we will have some number k, which is much, much less than the dimension of the original image. Here, n would be like the total number of voxels in the image. So we're saying that if the image is compressible and sparse in this transform domain, then the number of non-zero coefficients, or the number of significant coefficients in this domain, is much, much less than n. And it turns out that for many natural images, the wavelet transforms are very effective in compressing the real-world signals. But this can be optimized further. The different signals have different best transforms to use to compress them. So for example, there are signals that we encounter in MRI that are sparse in space, such as angiograms, where we have bright signals that are relatively flat in intensity inside veins here, and then a dark background, or a uniform dark background. So these signals are already sparse in space. They can be sparse in a transform domain, like we talked about on the previous slide. So an image of the brain here, it can be sparsified by taking it to a wavelet domain, or it can also be sparse in a finite difference domain. We don't have to restrict ourselves to just thinking about sparsity in space. We can also apply transforms to a series of images across time, and we can take advantage of the fact that some signals, such as cardiac images, because they repeat in time, they're going to have a certain high Fourier coefficients, and so then a set of cardiac cine images is going to be compressible in the Fourier domain. So here's an example of an image of the calf that is, and then we've applied different transforms to it in hopes of sparsifying it. Here's a discrete cosine transform, a wavelet transform, and finite differences. So if we take those transforms and then we threshold the coefficients by their amplitude. So here we take the top, in this column we've taken the top 20% by amplitude of the coefficients, top 10% and top 5%. Turns out we can really throw away most of the coefficients using any of these transforms, although different transforms will have different degrees to which we can compress the image. So for example here, it appears that maybe the discrete cosine transform or the wavelet transform significantly outperforms the finite differences, which tends to give you pretty large flat regions right away. Fourier transforms are going to be in practice worse than all of these because they don't take local differences, right? A Fourier transform, each coefficient in a Fourier transform is a weighted sum of all of the voxels in the image, whereas all of these transforms operate locally. Here's another example of a brain image showing how the discrete cosine transform and the wavelet transform are a bit more effective than doing finite differences in terms of how many coefficients you can throw away before you get significant loss of detail in the image. So the fact that we can medical images are compressible leads to a potential for a new way of doing things, a new workflow. So the standard approach, of course, in MRI imaging is to first collect all of the data and then compress it. So you take your signal, right? You take all your signals, you reconstruct an image from that. You have n samples all along the way, right? You record at least n samples from the scanner. You convert those into an n sample image, and then you take those n samples of your image and you apply some lossless, or at least visually lossless, compression approach to it before you store it on disk. So in compressed sensing, we try to skip this step, right? Can we instead, in compressed sensing, just take some number k samples, which is many, many less than the actual number we want to reconstruct, and then from that synthesize the entire set of voxels in the image. So compressed sensing is really a new way of thinking about things compared to the old way, which is the Scheinin-Nyquist sampling, which says that you have to have at least n samples if you want to reconstruct n samples. But this is really based on math for the worst case for any band-limited data, right? By band-limited, we mean the width of the signal in the image domain for MRI. But in compressive sampling, we exploit the fact that sparse signal statistics can be recovered from a small number of non-adaptive linear measurements. By non-adaptive, we mean that we don't have to even necessarily adapt the samples or the system that we're taking to each object that we're scanning. And so what we do here is we integrate sensing, compression, and the processing, and it's based on concepts, sparse MRI is based on concepts of incoherency between signal and measurements, and we're going to talk more about what we mean by incoherency as we move forward here. Okay, so to introduce the math of compressed sensing here, let's say that we have a real-world signal x, which has dimension n, and that it in some transform domain is sparse in that it has only k significant coefficients, where k is much, much less than the total number of voxels, for example, in the signal. And then what we're going to do is make m linear projections of this signal using some sensing matrix phi here, where m is somewhere between k, the number of non-zero coefficients in the transform domain for x, and n, the total number of samples in x. So we can represent our measurements as the set of samples y, which has length m, is going to be equal to the sensing matrix. So in MRI, the sensing matrix is the Fourier transform, times the overall signal, which is this x. This is the vector x in the transform domain, where you can see that we only have k non-zero coefficients. And then we weight, so these are the coefficients, we weight them by each basis function in the sparse basis. That gives us the image domain signal at this point, and then that signal is what is multiplied into our Fourier system matrix. It gives us our measurements. Okay, so what we're going to do here is manipulate the math a little bit. So here's our image domain signal representation. But we can similarly absorb the sparse basis matrix into the sensing matrix to get the total sensing matrix here. So again, x is in the transform domain, like not the image domain, but some transform domain such as the wavelet transform domain. So we're going to pull the linear measurement matrix and the sparse basis matrix into one matrix, multiply them together, and that gives us the total sensing matrix. Okay, so in order to work well, compressed sensing sets some requirements on this total sensing matrix that we have defined. The first requirement is the restricted isometry property, which says that the total sensing matrix must be length preserving approximately, in that any signal multiplied into this matrix has to have approximately the same amplitude as the original signal itself within some epsilon. It also has to have this property of incoherency, meaning that which mathematically means that it's almost orthogonal. So that is, if we take the transpose of this matrix and multiply it by itself, then we get approximately an identity matrix, which means that if we take any of the linear measurement functions in this sensing matrix and multiply it by any other one, then we're going to get approximately 0, or much, much less than 1. So what is essential here is that x is sparse. The original signal in the transform domain is sparse, but that the measurements are not sparse. That is, we cannot end up with a set of measurements that is mostly 0 also. It won't work in that case. So some examples of this would be things like spike Fourier signals or spike random signals that you might get if you had a sinusoid as a function of space, and then took a Fourier transform of that, you get a spike somewhere. You would not be able to reconstruct that signal well using compressed sensing. Okay, so now we have our definition of the forward operation, where we're going from our signal going from our original image data that we care about reconstructing to the k-space data that we're measuring under this total sensing matrix model. How can we recover this x? So what we are given is the data y, which has length m, right? We take total m samples, which is much, much less than the total number of samples in the image we're trying to reconstruct, right? So this is a short vector, and then we have this long vector that we would like to recover from it. So overall, this system is underdetermined. But there's hope, because we know already that x is sparse, right, as we defined from the beginning. So what we can do is try to enforce sparsity in the solution for x. That is, we're only going to consider solutions x that are sparse. Okay? So how can we enforce it? Well, a typical way of enforcing something that you care about, some feature or characteristic that you care about in a signal that you're reconstructing, is to use regularization or some kind of minimization. So one thing we can do, the first thing we think of to do, is to use the L2 norm. That is, we try to find among all the x's that are consistent with our data, we try to find the x that has the minimum L2 norm. This is a simple norm mathematically to use. It gives us minimum energy, and it also gives us conveniently a closed form analytic solution. It's very fast. However, it's wrong. It will not give you a sparse result. L0 norms are actually correct in that L0 norms, an L0 norm is just the sum of non-zero values in a vector. The L0 norms are correct, but they are very slow and difficult to implement. So in this case, we would replace the L2 norm that we're trying to minimize with an L0 norm, and this would give us a sparse result if we could solve it efficiently, but it's very difficult to do. L1 norm turns out to be the best balance of these two, in that it's still a correct norm to use and that it's sparsifying, but it is also tractable, and you can implement efficient algorithms that minimize the L1 norm of a signal, subject to the signal being consistent with measurements. Okay, so what we can use here to minimize the L1 norm is linear programming, which is relatively fast. It's of course a lot slower than just a normal gridding reconstruction, as we've been talking about in this class, but it's still relatively fast and tractable. And it turns out then that you need m is approximately k log n, which is still much, much less than the total number of signals measurements. And an L1 norm is just equal to is equal to the sum of absolute values of the vector x. That is, x1 equals sum over I equals 1 to n of absolute value of xi. So here's a three-dimensional illustration of why L2 norms don't work for compressed sensing signal recovery, but L1 norms do. Okay, so let's say that we have this true vector s that we're trying to recover from some measurements. And S has length 3. It's three-dimensional, hence we can plot its position in 3D. Okay, so S is the true point, and it has one non-zero element along this axis, which I guess by right-hand rule would be Y. And what I'm showing here then is the intersection of the L2 ball, right? This is all of the vectors in this 3D space that have the same norm, that have the same norm and intersect, that is, they touch this green hyperplane, which is the set of solutions that are consistent with the data, right? So the solution will always lie on this green hyperplane if we enforce data consistency, and so then minimizing the L1 or L2 norm is going to be equivalent to finding where this ball of uniform norm intersects with this plane. Okay, so with an L2 norm, that point happens right here in this case, at this point S hat. But that is obviously far away from the true solution S, whereas with an L1 norm, we the L1 norm ball looks like this. It's a polyhedron, and it intersects the green hyperplane here at the correct location. So again, this is the ball of all points that have L1 norm less than of the same amplitude. And if we're trying to minimize it, then we're trying to shrink this ball as much as possible while still finding where it intersects with the green hyperplane. So this is the smallest. This is the ball of points with smallest L1 norm that still intersect with the hyperplane, and it turns out that they do intersect with the set of possible solutions that are consistent with the data at the correct location where S is sparse. And in general, an L2 norm is almost never going to give you a sparse solution, where an L1 norm almost always will. So we can now define a nonlinear sampling theorem, which is an alternative to Shannon's theorem. So let's say that we have a signal f, which is in the Fourier domain and is supported. That is, it's non-zero on some set of points omega in the Fourier domain. What Shannon-Nyquist theorem says is that if omega is a known connected set with size width b, then you can make exact recovery of the signal f from b equispaced time samples. And then you can do a linear reconstruction to get the signal back by sync interpolation. Alternatively, now we have this nonlinear sampling theorem where omega can be an arbitrary unknown set of size b, okay? And we can make an exact recovery from about b times log n almost arbitrarily placed samples of the signal, and then we can recover the signal exactly by nonlinear reconstruction using convex programming. So putting this together, what do we need to do a successful compressed sensing acquisition and reconstruction? We need a compressible signal where we have at most k significant coefficients, where k is much less than the overall size of the image, n. We need order k incoherent measurements of that signal, that is measurements that lead to incoherent aliasing in the transform domain. So that is, while we get incoherent aliasing in the image domain, what actually matters is that we have incoherent aliasing in the transform domain, which is often, for example, the wavelet domain. And we can achieve this by randomly undersampling k-space. And then we need to recover the signal by solving a special nonlinear convex optimization problem. Okay, so now I'd like to give you an intuitive illustration of how compressed sensing works. So here is a signal we're pretending this is like the inside of a scanner bore, and let's say that we have like 3 point sources of signal, right? These could be like little balls of water or something like that, of different strengths here. So we have this blue guy here is like a larger ball maybe. Here is a red one with a little bit smaller, and yellow is a little bit smaller still, and there are different positions along this spatial axis, right? So in this case, the signals here are already sparse in the actual spatial domain, right? So we don't need a sparsifying transform for this particular illustration. Okay, so if we're going to measure signals if we apply a gradient along this direction, then we'll measure signals that look like this, right? Because we have 3 point sources, we're going to get a sum of 3 sinusoids in time. Now, Nyquist says that if we sample these temporal waveforms uniformly and sufficiently finely, then we can reconstruct the exact signal, right? So this is a picture of Nyquist. And then if we take the inverse fast Fourier transform of that, we can get the true signal back exactly. Okay, but what happens if we want to accelerate the scan by reducing the number of samples that we acquire? So let's say that we do the naive thing and sample uniformly, right, as we do in, for example, parallel imaging. Well, in that case, of course, we will get, after we do an inverse FFT, we will get coherent aliases, right? We'll get replicas of the objects. And here we're saying that the yellow object perfectly aliases on top of the blue object. And so now we are sub-Nyquist. There it is, Nyquist is underwater there. And so now we have this ambiguity, for example, about where this signal comes from, right? Where the signal in this bin of the reconstructed image comes from. Is it from the yellow point or is it from the blue point? We have no way of knowing. Okay, but now let's say that we sample randomly, right? So we space our samples randomly in time. What we're going to get then is we're going to get incoherent aliasing that looks more like noise. Now, that doesn't mean that some of the features are still going to be sort of underwater here, right? That is, you will definitely have features that are underneath the aliasing of other features. Okay, but now we can start to make some progress, right? Because at least the stronger features will be above the aliasing in general. And again, the aliasing here looks like random noise. But of course, it's not noise. So how can we get the signal back? What we can do is set a threshold. So we set some threshold such that just a few of the coefficients of our signal are above that threshold. Then we zero out everything else. Right? We only take those points that are above the threshold and we set to 0 everything else. Then we project those signals back through our measurement matrix back to the domain, and then we obtain all of the aliasing that is due to those two signals that were above the threshold, right? So now we have both those signals and we have all the aliasing that they generate. Well, what we can do then is subtract off that set of alias signals from the original input signal, and we are left with just the signal and the aliases from the lower point. So now we can see the lower point up above its own aliases. Then we can set a lower threshold, and we can recover that point. And now we have a perfect reconstruction again, even though we've taken many fewer samples than Nyquist would have us take. So here's an illustration for an actual image of the familiar GE logo phantom that you guys have seen before. So let's say that we take random samples of this phantom's k-space data. What we're going to get then is random undersampling. What we're going to get in the image domain is incoherent aliasing. Then we will apply our iterative nonlinear reconstruction that enforces sparsity. So it enforces both consistency with the data and sparsity. That is, it minimizes the number of non-zero elements in the resulting estimated signal while forcing the signal to be consistent with the data. And what's important here is that when we move to a transform domain, so for example, this is a finite differences transform domain, that the aliasing appears as random noise in the transform domain. And here are the recovered coefficients that we get if we do this. This then leads to a final result that does not contain any of the aliasing. So stated a bit more vigorously then, here's the problem that we're trying to minimize. What we're trying to do is minimize the L1 norm of the transform of our image in some transform domain. And so this is equal to the sum of non-zero it's equal to the sum of absolute values of the coefficients of m in this transform domain, be it finite differences or some wavelet domain, subject to the data being close to the estimated image m times the Fourier matrix, right? So for MR, this is our measurement matrix F. This is in the image domain, so we multiply m times the Fourier transform and compare it to y. We're saying that the L2 norm of these differences has to be less than some epsilon. So overall, this bottom term here enforces data consistency. It requires that our reconstructed image is consistent with the data, while the top term here enforces sparsity, where again m is the image we're trying to reconstruct, and phi is is a matrix that represents the wavelet or whatever transform that you're using. So then we take m here and we multiply it by phi, and that gives us the coefficients in the transform domain, and it is in this domain that we calculate the L1 norm. So one way to implement this is by transforming it into a regularized reconstruction optimization problem, where we set some parameter lambda that essentially is a function of epsilon on the previous slide. So the smaller epsilon is, the smaller lambda has to be, because you want to enforce data consistency more and more. So what we're trying to do then is minimize the sum of these two terms. This is a regularized reconstruction problem. And one simple approach to do this is using subgradient descent. So you take the derivative of, you basically calculate a vector of derivatives of this objective function, which this is the expression for the data consistency term of the gradient where the gradient is the vector of derivatives with respect to m. This is the gradient of this function with respect to m, and this is the gradient of the regularization function with respect to m. And then you pick some step size, and you step along the negative gradient direction, right? Because the gradient or the derivatives point along the direction that the function increases. So if we want to decrease the function, we want to step along the negative direction. And so at each iteration, I plus 1, we take the previous iterate and we subtract off some scaled version of the derivative at the previous location. There's lots more approaches that can be more efficient and converge better than this, but this is a very simple way that you can achieve this reconstruction. And so you can do nonlinear CG, you can do iterative thresholding, which is what you're going to do on the homework, and there have been many other approaches proposed. But the cool thing about MRI is that it's really a natural hardware for compressed sensing, right? That is, we have complete control over the design of the experiment via our ability to control the gradient waveforms and where we go in k-space, such that we can implement incoherent k-space sampling that is well suited to a reconstruction that exploits sparsity of the image we're trying to reconstruct in the transform domain. So now let's talk about incoherent sampling, how we can design acquisite sampling patterns that are better or worse for compressed sensing. So we need some kind of, for the goodness of a given sampling pattern, we need some metric of incoherency. So you can look at the point spread function of the sampling pattern, and you can also look at the transform point spread function. So the point spread function is the Fourier transform of the weighted sampling pattern in the spatial domain, whereas the transform point spread function is the transform in the wavelet or whatever transform you're using to sparsify your image. And so we'll talk about here some practical incoherent sampling schemes. So again, to illustrate the difference between PSF and TPSF, the PSF or point spread function of a given acquisition pattern would be taking the k-space domain sampling pattern and then putting a 1 at each location in that pattern. Then you take an inverse Fourier transform, and what you're going to get is a spike in the middle of space, because that's effectively sampling a uniform pattern, so you'll get a big delta function in the middle of space. But then a lot of incoherent aliasing if it's a random sampling pattern. And we can look at the goodness sort of this pattern by looking at both the maximum side lobe amplitude, this is taking a profile across one direction of this pattern, and then the RMS amplitude of the aliases. And one thing to note here is that this is essentially equivalent to taking a delta function in space, then calculating its forward Fourier transform, and then undersampling it with this pattern, and then going back to space and looking at what the aliasing pattern was that you got. Similarly, a transform point spread function is obtained by putting a delta function somewhere in the transform domain, be it here the wavelet domain, for example. Then you take an inverse discrete wavelet transform and to get to the image domain. Then you take an FFT of that to get to the k-space domain. You apply your undersampling pattern, and then you go back to the image domain via IFFT, and then you go back to the discrete wavelet domain, and you get both that spike and the aliasing that it generates, right? So here, at this point, then we have the transform point spread function. Now, one critical consideration here is that signal is generally not uniformly distributed in k-space. That is, the coarse scale is generally not sparse, right? So if you look at any real-world signal, yes, it'll be sparse in the higher frequency coefficients in k-space, and usually in the finer detail coefficients of some transform, for example, of the wavelet transform. But it will actually be fairly dense in the middle and not very sparse. So what we can do to compensate that is to use variable density trajectories measurement trajectories, which equalize the interference between the low frequency and the high frequency signals. So here's a uniform density sampling pattern versus a variable density sampling pattern, where the variable density has a little bit larger, has a little bit higher, a little bit fewer samples in the outskirts of k-space, but is more densely sampled in the middle of k-space. And this can significantly improve the result because you get better interference at all scales. Now, pure random sampling is really impractical in MRI, right? We don't, every time we scan, want to make up a new random sampling pattern, and we wouldn't want to have any sort of variations between subjects in terms of scanner performance if we accidentally stumbled across a very poor sampling pattern. So instead, what we do is design effectively random sampling based on the incoherency of the point spread function and the transform point spread functions. And we also try to consider patterns that are efficient for hardware and application in terms of not requiring very different, in terms of considering other effects such as gradient eddy currents on k-space trajectory position error and in PNS and things like that. And then we also, of course, consider the actual application that we're looking at, and that can really inform what the design of the trajectory of the sampling patterns should be. And of course, we look for robustness in particular, such that it always works for every subject. We really tailor the trajectory for every application, whether it be a Cartesian or a spiral acquisition, and based on what clinical indication you're looking at. And then you randomly perturb generally the standard acquisition to be effectively random. And you try to make this as minimally invasive a procedure as possible. That's generally how we can get these sorts of things adopted. So the most widely used acquisitions in MR are Cartesian. And you have three basic types of these acquisitions. You have 2DFT acquisitions of a single slice. You have multi-slice acquisitions, where you take an independent plane in k-space for every slice. And then you have 3D Fourier transform acquisitions, where you are measuring samples in the three-dimensional Fourier transform domain. And in each case, we can apply random sampling. We can by randomly removing phase encoding lines. This is a very simple thing to do, and the remaining samples are still some fixed delta or integer multiplied by some delta away from each other in every case, which helps with robustness in terms of eddy currents and such. So we can from the 2DFT, we can just randomly drop phase encoding lines. In the multi-slice case, we can maybe take different sampling patterns on different slices. And in the 3DFT case, we can take also different patterns in different k-space slices in the kz dimension. Okay, and each one of these really gives us enables different degrees of acceleration. So if we look at the 2DFT case and we calculate the transform point spread function by putting a delta here and then transforming it to the image domain, the k-space domain, applying the undersampling pattern to it, and then looking at what we get back in terms of aliasing. If we add a delta function in the coarse scale, then we get some pretty large side lobes here, and same with the fine scale coefficients. If we do this with multi-slice, we can reduce the side lobes somewhat compared to the 2D case, right? But they're still fairly large. But really, the 3DFT case is the most amenable to this type of compression, because here we can sample randomly in two different dimensions, that is kx and ky, ky and kz, whereas kx then is always uniformly sampled, and here we're looking at the ky and kz dimensions in the transform domain. And you can see that for both the coarse scale and the fine scale, we have significantly reduced side lobes and much better incoherency when we're able to undersample in multiple dimensions. So each one of these here is undersampled by the same total amount. Non-Cartesian trajectories such as radial and spiral give us some additional degrees of freedom for implementing incoherent sampling. So because you can easily undersample in 2 dimensions, even a 2D scan. So a very popular application of compressed sensing is radial sampling, because radial sampling already, if you just uniformly undersample, gives you a relatively good point spread function, side lobe amplitudes. And if we go to spiral, we get something similar. It has a similar property. And if we go to variable density spiral, that improves some more. And if we then further randomly perturb the spiral, we get an even lower side lobe here. But overall, the best strategies use some form of variable density sampling that is more dense in the middle of K-space versus the outer parts of K-space, and they minimally perturb the readout for stability. So here's a simulation that we can do to look at some of the different acquisition approaches. Here we've defined a simulated phantom object with 3 different intensity amplitudes. So here's 1, 2, and 3 different feature sizes in terms of numbers of connected voxels, and the image matrix here is 100 by 100. Within that 100 by 100 matrix, we have 5.75% of pixels are non-zero, and 4.25% of the finite differences are non-zero. And our target here is going to be to look at what artifacts we get with random undersampling, followed by different reconstruction approaches. Okay, using the same total number of samples, we can do a low resolution acquisition, or we can zero fill or we can do a random acquisition and use zero filling or compressed sensing with total variation penalty. That is total variation is the sum of is the L1 norm of the finite differences. So here's the low resolution results, and you can see that the trade-off here at a factor of 20x is a loss of resolution, obviously. If we do zero filling, we really can't make anything out, and if we do compressed sensing with total variation, we can make out some of the larger objects, but most everything is lost. If we do a factor of 12, then we can start to recover some of the features, and this compressed sensing starts to give a more reasonable image. Zero fill is still completely useless. And if we go down to 8x, then we can get a perfect reconstruction, and whereas the other two still are not really acceptable. The trade-off, of course, with low resolution, again, is that you get a loss of resolution. If we do an acceleration with zero filling, then we get a loss of apparent SNR because of the incoherent aliasing. With CS reconstruction, the acceleration leads to loss of low contrast features. That is, some of the features in the image may be thresholded down because they're too small. So here's an example of loss of resolution where these two objects connected to each other because of insufficient resolution to tell them apart, whereas if we went to a lower acceleration factor where we acquired some of the higher frequencies, you can start to tell them apart. The trade-off again with zero filling is the loss of apparent SNR, right? So you have, for example, in the 20x case, you have features that are completely washed out that then appear at lower acceleration factors. Whereas in the CS case, you have loss of low contrast features. So a darker feature here, for example, may not make it past the threshold for CS reconstruction at higher acceleration factors. Now, if we further take the compressed sensing total variation and apply it to a variable density acquisition, we can see that we get much improved reconstructions here, right? Because now we have better equalized the sampling according to the distribution of this underlying image signal. Okay, so we'll finish out the lecture here with a survey of different compressed sensing applications. So one of the early applications was doing 3D Fourier transform angiography. So angiograms, as we alluded to earlier in the lecture, are truly sparse. That is, you have bright vessels on top of a dark background of tissue that is nominally completely suppressed. They sparsify well with finite differences, and scan time is often crucial because you're trying to look at the dynamic flow of blood. So here's an example of an angiogram where we have done 10x acceleration on the readout, and then compared zero filling to compressed sensing plus total variation. And you can see that that as a function of acceleration factor, overall the compressed sensing is quite superior to the zero filling, which has a large background signal compared to the vessels. Here's another case where the acceleration with compressed sensing enables you to still accurately reconstruct certain thinner diameter vessels compared to a low-res acquisition where they appear disconnected. So in this case, compressed sensing was applied to improve spatial resolution subject to a fixed scan time. Here is a 3D-FT brain scan with spoiled gradient echo, where they did 2.4-fold acceleration in the two phase-encoded directions and used the wavelet basis as the transform. And you can see that the original image and the CS wavelet reconstruction are nearly indistinguishable, with the CS wavelet appearing a little less noisy. We can do multi-slice fast spin echo reconstructions of the brain as well. Head scans, of course, are the most common MRI exams, and most brain scans are multi-slice. That is, you excite and receive signal from one slice at a time. You can apply different sampling in the different slices, and then apply the transform across the entire 3D volume during the reconstruction. And this also then results in a reasonable reconstruction with wavelet based CS reconstruction. So here's an example where in the multi-slice direction, again, this is the sampling pattern as a function of ky. We drop out phase encodes as a function of ky, and then we have a different pattern for every z location, that is every slice. And you can see that the 2.4 accelerated CS wavelet reconstruction is able to recover an image that is nearly the same quality as the fully sampled Nyquist acquisition, again with no parallel imaging used here. And for multi-slice acquisitions, it's really much better to use the variable density different sampling patterns on every slice, as you can see. So that's this pattern here versus using the same pattern on every slice. So here's a matrix of images that's obtained using each undersampling scheme here. So here's variable density with the same patterns, uniform density with the same patterns, and completely random sampling. And you can see that overall, really, the variable density with different patterns on different slices wins here. We can also develop special acquisitions and reconstructions for dynamic imaging, for example, of the heart. So that is, smooth and periodic signals are sparse in wavelet Fourier space. That is, you use wavelets in the spatial domain and Fourier transform in the time domain, because we're assuming that, for example, it's like a heartbeat that is regular, right? It beats once every second, something like that. So then we can use wavelets across space and then a Fourier transform across time, and that can give us sparsity in those two domains. And we can start to design incoherent sampling patterns in the ky time dimensions, right? So here's a spatial dimension and the time dimension. So we randomly phase order the samples in kt space, and this gives us a point spread function where we again have a large peak in the frequency in spatial dimensions and relatively lower side lobes. Whereas if we had done uniform undersampling of kt space, we would get large delta function side lobes, large replicas within the field of view. So here's the results of this simulation. Here what we did was reconstructed this data with fourfold acceleration, where we had 16 frames at 4 milliseconds per frame, and used a wavelet transform to provide sparsity in the spatial domain, and a Fourier transform for sparsity in the temporal domain. A sliding window reconstruction, just looking at a single time frame here, gives lots of ghosting, as you would expect. The sliding window is just taking a certain amount of k-space data and accruing it into each image, and just moving that window along through time. And if you do this KT sparse approach, then you can reconstruct something that's very close to the ground truth. Here's some data from an actual dynamic heart imaging using balanced SSFP, short TR 4.5 milliseconds, a resolution of 2.5 millimeters, 9 millimeter slices, and then 7-fold acceleration without parallel imaging to achieve a 25 frame per second temporal resolution. And you can see here that compared to sliding window, KT sparse is able to remove most of the aliasing artifacts, and you can really see in time the coherent parts of the heartbeat. We can also apply undersampling in the spectral domain and do sparse spectroscopic imaging. So spectroscopy is also a form of like dynamic imaging. It can be when you're doing injected carbon-13 acquisitions. So here's an example of a compressed sensing reconstruction of dynamic carbon-13 spectroscopic imaging, showing a 2-fold accelerated compressed sensing reconstruction compared to a full data reconstruction. The x-axis here is frequency, and then these are different voxels. So these are the spectra at different voxels, right? Each box here represents a different voxel over this grid. So to summarize, we have this new sampling theory, this new nonlinear sampling theory that is the sort of a continuation of Nyquist theory, but allows us to get to accelerated MR imaging because it says that we can acquire many fewer samples than Nyquist would have us sample. It can be implemented in practical applications, and there are many applications and possibilities for it. There are still tons of open problems in this space. I mean, these slides that I'm using, these are from Mickey Lustig, by the way, at Berkeley. He used to be at MRSRL, and now he's at Berkeley. There are lots of open problems in this space that still have yet to be addressed. So then we are going to have a few problems on compressed sensing on homework 4. Looking forward to working with you all on that.